Hello, everybody. So this is week 2, lecture 3, and what we're going to be talking about today is going to be uh, evaluating limits from tables. So these are going to be tables of function values. Um, so as far as learning objectives go, oh no, it's doing the same thing as the previous lecture. Um, as far as learning objectives go, this lecture will help you meet the following course learning objectives. These are the same as the previous lecture and the same as the next lecture. We're going to be doing SLOA, which is apply the concept of limits. And how are we going to be doing that? Well, by evaluating limits using appropriate techniques. The techniques in this section are going to be different than the previous lecture. And we're going to be using properties of limits. And also, we're going to be making appropriate use of available technology. So the appropriate technology that we're going to be using today are going to be some websites for, basically, we're just going to use them as a calculator because we can. It's going to be faster than using an actual calculator. So let's go ahead and get started here. So as far as an introduction, the subject of calculus is based on, no, stop. The subject of calculus is based on the concept of limits. This is our second lecture on this topic. In the previous lecture, you learned the definition of the limit and how to tell what the limit is by looking at a graph. In this lecture, we're going to estimate limits numerically using a table of values. And then we're going to guess the exact limit from the table of values that we make. So in the previous section, we looked at graphs. In this section, not looking at graphs. Okay, so this is going to tell us how we're going to go about doing what I said we're going to do. So I've got a limit written here. This is just to look at while we think about these steps. So this says limit as x approaches 4. This is a two-sided limit because you don't see the plus or the minus superscript on the 4. So limit as x approaches 4 of x squared minus 16 divided by x minus 4. And so you might notice that there's kind of a little bit of an issue here. For example, x is supposed to approach 4. If you tried to plug in 4 here, you're going to see that there's a problem, right? If you put the 4 in here, 4 squared is 16. 16 minus 16 is 0. So the top would be 0. And if you put the 4 in on the bottom, 4 minus 4 will be 0. So you're going to get 0 divided by 0, which seems to be an issue. But if you remember the previous lecture, what you do when you're calculating a limit is you're tracing the curve over to the point. Do you remember that when we traced a curve over to a point? And we said that it didn't matter if there was a hole in the function when you get to that point. What matters is if you trace the curve from the left and you trace the curve from the right, you get to some y value. That's all that matters. It doesn't matter if there's a hole in the function there. So this function here happens to have a hole at x equals 4, and we don't care. That's too much detail for right now, but let's go ahead and look at how we're going to try to estimate a limit using a table of values. So listed here, the function f of x is x squared minus 16 over x minus 4. Yes, it is. X is approaching 4, right? X approaches 4. We should consider x values that get closer and closer to 4, right? That's the equivalent of tracing the curve over to x equals 4. So what we're going to do is we're going to make a table of values. And our table of values are going to use these values for x. 3.9, 3.99, 3.999. Why are we going to use those? Well, because x is supposed to approach 4. So 3.9 is close to 4. 3.99 is closer to 4. 3.999 is even closer to 4. So 3.999999, these are getting closer and closer to 4. That's what we're supposed to be doing when we're evaluating a limit. But 3.9 to 3.999, those are all close to 4 on the left-hand side. We know that to calculate a limit, we should be looking at the left-hand side and the right-hand side. So the left-hand side of 4 is 3.99 stuff, And the right-hand side of 4 is going to be like 4.1 type stuff. So we have these numbers as well, 4.1, 4.01, 4.001. So those numbers right there are close to 4 and getting closer to 4, right? 4.1 is kind of close. 4.01 is closer. 4.001 is even closer. So these numbers just get closer and closer to 4. So we've got 3 that get closer to 4 on the left side and 3 that get closer to 4 on the right-hand side. And that's what we're going to use as x values to make our table of function values. All right, let's look at the next slide. So this is what it would look like. So we're going to be considering the same function. So the limit as x approaches 4 of f of x, where f of x is x squared minus 16 on top, x minus 4 on the bottom. We've decided which function values, sorry, I said function values here. This is wrong. This should say decide on the x values to use. The x values we want to use are 3.9, 3.99, 3.999, 4.1, 4.01, 4.001. So you make a table of values. You have a column for the x values where you put those x values, the 3.9 up to 3.999, and the 4.1 up to the 4.001. Now you'll notice if you look at this column here that I have 3.9 up to 3.999. And then when I go to the 4s, I put 4.001 first instead of 4.1, right? Like you would think that 3.9, like 999,999, you think I would go 1, 1, 1, or 1, 0, 1, 0, 0, 1. But I'm not. The reason I'm doing it this way is just because these two values that you have in the middle here, 3.999 and 4.001, these two x values are the closest to 4. And if they're the closest to 4, they're going to give us the best estimate for our limits. Okay, so we make this table. We have a column for x. You put your x values that are close to 4 there. In the other column, you need to actually calculate the function values. That means you need to take the x value and plug it into the function given for the limit. So I'll show you how to do that real quick. This is going to be my recommended way to do it as well. So if you haven't seen this site before, now you have. There's a site called wolframalpha.com. This is a freely available math software. It's a website, but there's a lot of software under the hood. It can do very complicated processing. We don't need it to do anything super complicated. I just want it to calculate some values for me. So here's how I would do it. Our function is x squared minus 16 over x minus 4. So I would say I want it to evaluate x squared minus 16 divided by x minus 4. Use parentheses where appropriate. Notice how I typed in the caret there. And then I'll just say what x value I want it at. So I'll say evaluate this at x equals 3.9. Okay, so if I just hit enter here, I get the result of 7.9. And this is a very convenient way to calculate your results, because if you need to change it to calculate it at a different x value, you don't have to retype anything. You can just come up here to where the 3.9 is, say 3.99. And the result is 7.99. But 3.999, 7.999. Right? So do you see how fast it is to calculate values this way? You can certainly use a scientific calculator and just put in 3.999 in for your x values and calculate that. That's not super hard to do. But Wolfram Alpha will just make this process a lot faster. Okay, so this is how I would recommend that you do it. Come back over here and you'll see that my f of x values, I've got 7.9 to go with the 3.9. 3.99 goes with 7.99. 3.999 goes with 7.999. Then you have your 4s. I'll go to the bottom value first, 4.1. The result is 8.1. Going back over to the lecture slides, you see I've got 4.1, 8.1 right there. And so you calculate these. So you figured out your x values that you want that are close to 4. You calculate your function values, which are close to whatever. And then what you're supposed to do is look at these results here and try to guess at what this limit actually is. Okay, so what you're going to do is say, well, which of the x values are closest to 4? I should have made this big again. So you should, whoa, let me get back to where we were. There we go. So the x values that are closest to 4 are these two that I put in the middle, 3.999 and 4.001, right? And the function values that we got there are 7.999 and 8.001. So you should be able to look at these function values, which go with the x values close to 4, and guess that this limit is probably 8. Okay, so you look at these function values and guess 8 based on what you see here. Okay, and that process is just how you're going to calculate, or rather estimate, function values using a table of value. How you're going to estimate limits using a table of function values, I should say. Now, if you were to graph this function, here's what you'll see. So I'm going to use a different program here. So this is Desmos, which is desmos.com and /calculator. But if you don't put the /calculator, you'll just have to click a button to get in here. If you were to graph this function, which was x squared minus 16 divided by x minus 4, you'll see it looks just like a straight line. And if you go over to where 4 is and you try to click on the curve, maybe I can make this a little bit bigger here. If you click on the curve, you can see I can drag a point around. And if I go over to x equals 4, you'll see something happen as I get close and close. 4 undefined. Right, do you see that? 4 undefined? That's because we know you can't put in 4 here. But you can also see that even though you can't put in 4, if you get close to 4, you can see the y values going to 8, right? From both sides, they go to 8. At 4, it's undefined, but a little bit to the right, you're close to 8, and a little bit to the left, you're close to 8. Okay? So that's what it looks like on a graph. You would have been able to do this graphically in the previous section, but with the table of values, we get this, and you should also know that the limit is 8. Okay, so that's how this process works. So this here is just going to be some tips for making your tables, help you out here. So you can use any calculator you want. We do want decimal numbers here, not fractions. So you're not looking for like 5 7/8 or something for an answer. You just want decimal numbers. Okay. You should also write your numbers out to a few decimal points. You know, if your decimals go out a few decimal points, you should write them, right? Like you shouldn't say 7.99. You shouldn't round that to 8. You shouldn't round this 7.999 to 8 because you want to see how these are changing. And if you round your answers, you won't be able to see that. So do carry out your decimals to several decimal places so you can see what's going on. If you want, you should use a tool like Wolfram Alpha to save you time. There's an image here that shows exactly what I did. I just type in the function and I say at, and then whatever x value I want to evaluate this function at. So the other thing is if you're solving problems like homework problems then keep in mind that your answers are supposed to be, something you can guess at. So you're going to see whole numbers like we just had the answer 8. You're going to have answers like 8 or other whole numbers or simple fractions. So like 1/2, right? You should be able to tell when you see like 0.49999 or something that's basically a half. You should be able, you should know what 2/3 looks like, right? That would be like 0.66666. You should know what 1/3 looks like, and so on. And you should be able to see those and guess at what the fraction is if you see it in your table. You're not going to see numbers like this, like 5.5873368, showing up in your table, at least not when you get close to the limit, right? Like if I go back to a table here, these middle values are the ones that are closest to the real limit. The first one doesn't matter, right? So much. This could have been further off. It could have been like 7.5 or something, right? And if it was 7.5 and then 7.99 and then 7.999, we wouldn't care that this first one was 7.5, right? So you might see some weird numbers for the ones that are furthest away. But for the ones that are very close to x equals 4, you would expect the function values to be very close to the true answer. So these, when you look at those middle ones, those are the ones that should be close to something that you can guess. Okay, so you're not going to have anything super complicated for an answer, which makes guessing easier. So with that said, let's try to do some other problems. So this is just kind of backing off from doing the table right now, just to say something about functions that we should know. And that is, in the previous example, you saw that you could not plug in x equals 4, right? Because it was not defined. Just to remind you, right, it was this function, x squared minus 16 over x minus 4. 4 gives you a divide by 0. So that's not defined. So that function is not a continuous function. But a key here is going to be that if you have a continuous function, right? So if we go back here, if there was no divide by 0, right? So no x minus 4, if there was no divide by 0 there to worry about, and all we had was x squared minus 16, then there's no holes in the function, right? Remember when we look at Desmos, it's just a straight line here, but then at 4, the function is undefined. So that's actually a hole in the function. But a lot of functions don't have holes. And if they don't have holes, if there was no hole here, then it wouldn't say 4 comma undefined. It would say 4 comma 8, because that's where we are on the graph, is 4 comma 8, right? And the reason I'm making a point about that is that, going forward here, is that if you do not have these divide by 0 issues, then there's nothing stopping you from just plugging in your number. Technically, that's a rule for limits that we haven't learned yet, but the sooner you learn it, the more sense this will make. So like, look at this limit here. A limit as x approaches 3 of x plus 5 over x minus 6, right? And I say, what is this limit? It's very complicated. You could absolutely make a table of values here, okay? Like if x is approaching 3, you should be using like 2.9, 2.99, right? Or 3.1, 3.01. So you can make a table here. It will work perfectly well, okay? But another thing you could do is you can just say like, well, wait a second. This function has a divide by 0 at x equals 6. There's a hole at x equals 6 because of the x minus 6. There is no hole at x equals 3, right? This is a limit as x approaches 3. There's no hole at 3. So actually what you can do here is skip the whole table thing, and you could actually just plug the 3 in. If you want the limit as x approaches 3, just put a 3 in for x. And so if you do that, plug a 3 in for x, so you take the 3, put it in there, you'll have 3 plus 5 on top, which is 8. Plug the 3 in on the bottom, you'll have 3 minus 6, which is negative 3. So you end up with, down here, you'll see 8 divided by negative 3. And that would be your answer. Okay, negative 8 over 3. Because you can just plug in the 3. And the reason I'm bringing that up now is because the divide by 0 business is really what is stopping you from being able to do this in general. Okay, so on the example where we had the limit as x approaches 4 and x minus 4 in the denominator, there's a hole at 4. That's what made us have to do this. Okay. If there's no hole at 3, which there isn't, then just plug in 3. All right, so we're going to make more tables. And as far as examples go for what tables to do, we're going to do these tables that involve trig functions here. Okay, so these are limits that we want to do now because you're supposed to memorize these. You're supposed to memorize these limits and remember them for later. So the first one that we're going to remember is the limit as x approaches 0 of sine x over x. And again, you can't just plug in 0 because you end up with 0 divided by 0, which is undefined. But the limit as x approaches 0 of sine x over x is equal to 1. And there's a similar one for cosine. Limit as x approaches 0 of cosine x minus 1 in the numerator, x in the denominator, and that limit is going to be 0. Now, how do we know that the first one is 1 and the second one is 0? Well, we're going to do it right now, right? That's what we're going to use the tables for. We're going to calculate these, or we're going to estimate these using the table and just hope that we're right. Okay, now pay attention to this here. In future calculus classes, your instructors will assume you know these, especially the first one. Okay, limit as x goes to 0, sine x over x is 1. Okay, so yeah, so let's go ahead and work these out using tables of values. So let's think about this. We're going to do sine x over x first. So got some notes here. X approaches 0, right? It's a limit as x approaches 0. So we should take x values that are close to 0. So we're going to take 0.1, 0.01, 0.001. Those are close to 0. We need ones on the other side of 0. So negative 0.1, negative 0.01, negative 0.001. Those are the x values we want to use for our table. We need a calculator to use. I'm going to use Wolfram Alpha. You can see that I've got a screenshot there. And then we're going to guess at what the limit is. Okay, so here we go. Oops. So I've got my table of values right here. Remember, we're going to come up with that using Wolfram Alpha probably. I have something to say about it, but let me go here. So I can just say we're doing sine x divided by x at x equals, and you can't say at x equals 0 because it's undefined, but you can do it at 0.1. So sine x over x at x equals 0.1. I think the last time I said evaluate, but you don't have to. Wolfram Alpha will understand a lot of different things that you type in. So you type it in, and it tells you what it thinks that you typed, sine x over x, where x equals 0.1, and then it gives you the result. Now notice that the x here is in radians, not degrees. If I type degrees here, I think you get a completely different answer here. And if you use a calculator, like a pocket calculator, scientific calculator type thing, graphing calculator, make sure your calculator is in radian mode. On Wolfram Alpha, it just guesses at what you want, and it's usually right. you can type in radians or degrees if you care, right? So here I say x equals 0.1 radians. Well, I don't know why they're giving me the answer this way, so maybe I should leave that off. But 0.1, it should be in radians. Okay, so there we go. We get a result 0.998334. And if you come here, you see that on the lecture slide, x equals 0.1, sine x over x is 0.998334. So you work this out for 0.1, 0.01, 0.001. And if you do that, you'll see sine x over x 0.01, 999983. I mean, you could probably already guess that this is going to 1. If you put in another 0 here, Wolfram Alpha says 1. But this is actually, I put in 1, but this is not actually 1. It's just that it's really, really, really close to 1. And so the computer is telling you the answer is 1. It's actually like 0.9999999. Like, I think it's like 8 nines in a row. So like 0.999999998 or something. But it's so close to 1 that the computer is telling you 1 right now, because it has to round to a certain number of decimals. So that's why I've got 1 point there. And I think usually they put the dot there to indicate that there is a decimal, but it's so close to 1. All right, so if you filled out the table this way, again, you look at these middle two values here because they're the closest to x equals 0, and you see that the sine x values that we come up with are 1 and 1. So what do you think this limit is? Well, you think that the limit is 1. Okay, and that's how you do it. So sine x over x is 1. We can do the exact same thing for the other limit, which was the limit as x approaches 0 of cosine x minus 1 divided by x. And we're going to use the same x values, right? 0.1, 0.01, 0.001, negative 0.1, etc. You can use a calculator or a tool like Wolfram Alpha, and then we're going to guess at what the limit is. Before we look at the table, let's just go over here at Wolfram Alpha. And if you typed this in, you have to be careful to use parentheses appropriately to make sure you get what you want. Let me just actually, there we go. So whenever you type anything into Wolfram Alpha, always look at what the interpretation is to make sure that it actually understood what you typed the way you wanted it to understand it. So here, cosine minus 1 over x, where x is 0.1, we get negative 0.0499. So negative 0.04999. No, 995. And then you change this to a 0.1. And you see it's negative 0.00. So there's 2 zeros here this time. You make it 0.001. Now it's 0.005, 3 zeros, right? And what you should be noticing is that the closer this gets to 0, right? Like if I go like this, the closer this gets to 0, the x value, the closer the result gets to 0 when you plug that into your function, right? Negative 5 times 10 to the negative 6. So that would be like the result there that it just calculated was negative 0. Negative 6. So 1, 2, 3, 4, 5, 6. Right? Is that right? 1, 2, 3, 4, 5, 6. Yeah. So this is what it calculated here, right? So you can see that this is very, very close to 0 here. I don't know what's happening with the cursor. The closer this gets to 0, the closer this gets to 0. And of course, we were doing this on the other side as well. So on the negative side of 0. So you had to do negative 0.01, and then you get a positive answer. So if you look at your table of values on the next page here, you can see I filled it out. And you have your x values and you have your function values. And you can see, hopefully you can see that what's happening to these function values, right? 0, negative 0.049, negative 0.0049, negative 0.000, and then it was probably 49, but it rounded. And same thing on the other side. These first three are negative, the second three are positive. And if you were going to guess at what the limit is, you should look at these center values here, these two center function values, and say, looking at the pattern, these are getting closer and closer to 0. Okay. And that's what you'll guess at your answer for the real limit. So the limit as x approaches 0 of cosine x minus 1 over x is in fact 0. Okay, and that's how you make these tables here. It's not that bad, really. Okay, so you do have to do these on the homework, and yeah, there you go. One comment I will make about this is that make sure you understand too that when we look at this table here and we look at the values in the middle and then we say, oh, okay, this limit as x approaches 0 of cosine x minus 1 over x is equal to 0, really that 0 is still just a guess. Like how would we know, like the method that we employed here, what if the real limit was 0.0000007, right? That was the exact value. 0.0000007 was the real answer. Well, we didn't really have enough detail in our table to be able to tell that the answer is not 0.0000007, right? So when you make a table like this and you guess the answer, you're probably going to be right if it's like a whole number, like 0 or 1 or 3 or whatever. But technically you haven't proven that this limit is really 0. You've just done some math to convince yourself that it's 0. Okay, and that's why if you go all the way back in the lecture to when I described this process here, you'll notice that the language I used was we're going to guess the exact limit. So we're not calculating the exact limit, we're guessing at what it is. Okay, and notice in the first example we did, we said we looked at these function values and we guessed that the limit is 8, right? Because when you see the 7.999 and the 8.001, and you say that these are both close to the real limit, it makes sense to guess 8. It doesn't make sense to guess, 8.0000000, 35, right? Even though, technically nothing rules that out as a possible answer here, right? So we're just looking at these numbers and making a guess as to what the limit is based on what we think makes sense. Okay, so that's it for this lecture. In the next lecture, we're going to go ahead and we're going to learn to actually calculate these with proper algebra, right? We've done numbers, we've looked at graphs. In the next lecture, we're going to do algebra. So look forward to that, and I will see you then.